So I have put in the chat a link to a web page that I will follow for all the practical parts of this hands-on. At the end of this link, so if you scroll on the web pages, you will see that it's the last page. There is all the hands-on materials that is available and the projects that are completed and working. So if you wish, later on, you can download the material and reproduce exactly what I will do here. So this hands-on is proposing to show how to use in practice the STM32 ecosystem and tools to design what could be a real low-power project. This project is a simple bus system that operates down to stop mode. And what we will do is we will step-by-step design this project using what we call the cube firmware, so the HAL, low-level, and board support package libraries to manage the software of this bus system. You have seen in the previous demo of Jeff that we were reaching a nice application using RTC and the glass LCD and the stop mode. Here we will also use the RTC and the glass LCD, but we will, in addition, use the low power timer, the ultra low power comparator, and among the two projects, because in fact we will use two projects, one for the Nucleo and one for the Disco. On the Nucleo project, that in fact is optional because it's used to test Discovery ultra low power software. So the first project for the Nucleo, I will not detail it, I will skip it. In fact, I will just explain what it's doing. And this project on the Nucleo is using the DMA feature. So it's good to know that you can have the DMA operating while the core is sleeping. So and the Nucleo project will show this. And so at the end, we will verify the consumption using the ST Cube monitor power and the ST-Link V3 power. So this project, we can imagine that we want to build a simple bus architecture with one master panel that is visible here and several multiple end devices. And the end device is connected to the master panel thanks to two wires. You have the ground and you have VCC plus the modulated communication on the second wire. The modulated communication is quite simple. You have a bit 0 that is represented here in red, and the bit 1 is also represented here. So in fact, the difference between the bit 0 and bit 1, it's the duration of the low pulse. And the size of the pulse is in the hundreds of microsecond range. Actually, we will send some pulses, some bits that are 5 milliseconds wide. And with the Nucleo kit, we will change the duty cycle of each bit to simulate bit 0 or bit 1. And the duty cycle will be either 0%, which means that the line is idle, or 20%, 40%, 60%. So which will mean in practice 1 millisecond of low pulse, 2 milliseconds, or 3 milliseconds among the 5 milliseconds of the bit duration. Okay. Of course, for the real project, you will have to create your own proprietary protocol. So typically a start bit, some data, stop bits. Okay. And if you may wonder why it's important to have an ultra low power microprocessor to do this, or microcontroller, it's because if you multiply the number of end device, could be 100 end device, 200 end device, and all this is powered by the master panel, you can understand that it's extremely important to optimize the consumption of the end device. You can imagine this kind of connection for fire alarm, smoke detectors, things like that. So I will go quickly on this one. So it's just to say that I will use CubeMX to create the project and configure the hardware. I will use CubeIDE to debug and to add some line of code in the project. CubeMX and also CubeIDE are in fact using in background what we call the U0 cube library. At this moment on my PC, I have the 1.0.0, and as said, the 1.1.0 is already available on the GitHub and will be available on the ST website to be downloaded by CubeMX and CubeIDE. So when you start to CubeMX and CubeIDE, by the way, the cube firmware, the U0 cube firmware is not preloaded. So CubeMX and CubeIDE, they need to do an internet connection to retrieve the cube library on ST website. On my case, I have already downloaded the cube library, so you will not see that. But if you are not familiar with CubeMX and CubeIDE, you need to know that it's a tool that needs to access the cube library in order to be able to build the project. And also I will use, as Antoine, the cube monitor power to check the power consumption of the end device. And so the Nucleo kit and the discovery kit. So you can see that if I open my CubeIDE, I have already created the master panel and it's already flashed inside the Nucleo. And if I, just to show you how it will work, so it will be, the master panel will be used to test the end device, and the master panel is generating on this wire the PWM signals with the variable duty cycles. And to change the duty cycle, I need to press on the blue button. And if you see, this PWM signal is also connected to the green LED here. And if I zoom a bit so that you can see, if I press on the blue button to change the duty cycle, you see that the LED has brightness that is changing. So you can see that indeed the duty cycle is moving. Okay. So not do in detail the master panel, but I will explain you the principle. So the principle is each time you press on the blue button, as I did here, so you get an external interrupt. This external interrupt is connected to an IP that is inside the U0 that is called the DMA MUX. And this IP is generating a DMA request. And this DMA will fetch from the internal SRAM the duty cycle that you want to apply on the PWM. And it will be written in the capture compare channel 1 of the timer 2. And in fact, you will write either 0 or 20 or 40 or 60, depending on the percentage of low pulse that you want. And because the timer 2 counter is counting up to 100, and your comparison will be with 0, 20, 40, and 60, in fact, you are exactly, it's the percentage of the duty cycle of the bits that you are changing here when you press on a button. And while everything is running, the core is sleeping. I will not detail more. As I said, the master panel is available on GitHub if you want to download it and test it. And if you follow the cheat sheet here step by step, you will be able to reproduce exactly this master panel example. So I will switch now to the real Hanson that I am about to demonstrate. So this is the end device Hanson. So I remind you that the end device is supplied by the master panel. Is in the real life, it should be supplied by the master panel. In our example, in fact, I will use the discovery kit to simulate this end device. So the discovery kit is already powered. In fact, in order to do the demodulation of the signal that you will receive on this VCC bus, you would need to have some extra hardware, extra transistor. So this is not done. So this would remains to be done for a real project. So it's really a simplified project that we are designing here. Also, a real project, real end device would have to provide answer back to the master panel. You would have to tune maybe the way you reshape the PWM signals, because if you have several hundreds of meters on the line, the signal could be very distorted. So all this would still remains to be done for a real-life project. In our case, in fact, so we will use what is shown here. We will receive directly the PWM, so between 0 and 3.3 volts coming from the Nucleo board. We will send it to an ultra-low power comparator that will use on its minus inputs an internal voltage reference set to 1.2 volt. You could also use, for a real-life project, you could also use DAC output. There is an internal DAC in the U0. If you want to set another comparison level. And then this ultra-low power comparator will send directly the reshaped signal to the low power timer 1 on two input capture channel, channel 1 and channel 3. Channel 1 will be capturing the falling edge of the signal, and the channel 3 will be capturing the rising edge of the signal. And each time there is an edge falling or rising, you will get an interrupt, and the core will be woken up and will process the data. There will be also the activation, when there is an activity on the line, the activation of the RTC that will be used as a 1 second wake-up signal to check if the duty cycle has been changed. And if the duty cycle is updated, the new duty cycle will be displayed on the LCD. And also, if you go back to idle, if the line goes back to idle, the RTC 1 second wake up will detect this, and because there will be no more change in the input capture, and it will display that the line is back to idle. And after this, the RTC 1 second wake up will be stopped, and we are back to full idle mode where we are waiting for the next interrupt coming from the low power timer. Yes, okay, so let's start the project. So I will use CubeMX, as I said, which is the standalone CubeMX version. You have also a CubeMX inside CubeIDE. The only thing is that if you use the CubeMX that is inside CubeIDE, you cannot generate a project for another IDE, like Kale or EAR. So I will select the U083 here. And I will select the line, the U083 that is part of the discovery kit. So that's good. So now I will use CubeMX to do all the configuration, the needed configuration, except the LCD. I will explain why later on. So I will start by the 32 kilohertz clock. So on the discovery kit, there is crystal, 32 kilohertz crystal, so I can activate it. Okay, so let's do that. So inside the RCC, you need to activate the low speed external clock. And here you have several possibilities, but what I will take is the crystal because I have a real crystal on the board. Okay. That's good. So you see that the small schematic here, you have the 32 kilohertz that has been activated here. And now I will switch to the ultra-low power comparator. So just to maybe explain a bit what is this ultra-low power comparator, I have prepared some summary of the advantage of this component and how it works. So here you see that it's a component that can work even in stop-to mode. It has a ultra-low power consumption. So you have the data in the data sheet, the complete performance of this component. But for example, if you send a 50 kilohertz input square signal to it, you have a typical consumption of 1.2 microampere. And if you look at what we will use during this hands-on of this component, we will in fact use its input plus connected to an external port of the U0, and this is where we receive the PWM signal from the master panel. On the minus input of the comparator, we will use the 1.2 volt internal reference that is available on the U0, and we will send that directly to the low power timer that is also inside the U0. So let's switch back to CubeMX to do this configuration. So this is comparator 1. So you need to select for the input plus the external pin of the U0. So you see that it's visible here. It will be PA1. And for the minus input, we will select the internal voltage reference. Okay. And there is an extra thing that we need to configure. It's the speed of the comparator, because there are several modes of this comparator depending on the speed of the signals that you are sending to the comparator. In our case, because it's a 5 millisecond PWM signal, no need to select high speed. So we will put the comparator in ultra low power mode. Okay. And that's it for the comparator. So if I go back to where we are and go back to, in fact, the drawing, you see that we have done this, and we need now to take care of the low power timer that will receive what the comparator will send. So as for the comparator, I have few slides to explain a bit the characteristic of the low power timer. So the low power timer, it's a 16-bit timer. It has a very flexible clocking mode, and it can be clocked by the 32 kilohertz. This is what we will use, by the way. You can also, if you want, have no clock at all and be in what we call asynchronous counting mode, if you want to count external signals that is sent to the U0, but we will not use this. It can work even in stop 2. It has an ultra low power consumption, so I put a typical consumption from the datasheet, which is 1.71 micron per megahertz. But here we will clock it not at 1 megahertz, but at 32 kilohertz. And it has some timeout function for wake up from low power mode if you want to use that. And if you want to have more information on what we will use for the hands-on, it's visible here. We will receive from the ultra low power comparator the signal here on channel 1 and channel 3. This will be processed by the edge detector to detect rising and falling edge. And this will generate capture compare latch of the value of the 16-bit counter. This will also trigger interrupt. So this is why the IRQ here is highlighted. And regarding the clock, it's the 32 kilohertz clock that is called here kernel clock that we are using to clock the timer. So let's do that. So I go back to CubeMX. I finished with the comparator. So I go to the low power, to the timer section, and I click on low power timer. Okay. So here, what we need to activate the internal clock, the clock internal mode. And here, what we will use is the channel 1, as I said, for the falling edge detection, and the channel 3 for the rising edge. So here, we need to activate the channel 1, and we need to activate the channel 3. Okay. And in parameter setting, if you look at what is available, you see that the channel 1 and channel 3 are visible here. And what we need to do for the channel 1, we say that we want to capture the falling edge. So instead of rising edge, we need to select falling edge here. And that's all. That's all, except that I said I want to trigger an interrupt. So in order to achieve this, we need to, in the NVIC setting, we need to enable the interrupt. Yeah, maybe one word, you seen here that automatically when we selected the channel 1 and channel 3, you had the possibility for the input capture to have the comparator, the output of the comparator 1. It's also possible to select comparator 2. In our case, it's comparator 1 that is interesting for us, so we keep comparator 1. Okay, so that's all for the low power timer. You see, it's quite simple. The next IP that we need to configure because we want to use it, it's the real-time clock. So as for the previous IP, I have also 2 slides. So the RTC, it works in all low power mode. So you can have RTC in standby, in shutdown, and even in VBAT. So it's part of the backup domain, what we call backup domain, powered by VBAT. So if you switch off the VCC and you keep the power on VBAT, the RTC will continue to be clocked. It has an ultra low power consumption, put here figure from the datasheet. So it's 220 nanoamps. And it can provide the classical RTC information, so time of day, calendar, and you can also have programmable alarm and interrupts. And if you look at the block diagram, you see what we will use for this Hanson. We will have the clock, 32 kilohertz clock, that will be first processed by this asynchronous prescaler. Then it will enter in the synchronous prescaler, and you will generate what we call it will generate a 1 Hertz clock. This 1 Hertz clock will be sent to this wake up timer here, and it will generate a wake up interrupt every second. So this is why also you have the IRQ that is highlighted in red here on this block diagram. Okay, so let's do that. So I go back to CubeMX. I need now to select the RTC as a timer. I need to activate the clock source. I need to select the internal wake up. And if you remember the slide, to clock the wake up timer, there are 2 possibilities. The output of the prescaler here or the 1 Hertz. So what we will select is the 1 Hertz. Okay. So this is why here, in fact, I will take 1 Hertz as a wake-up clock. Regarding the wake-up counter, we will keep 0. In fact, it means that it's 0 plus 1 that will be used to generate the wake-up interrupt. So every second you will get a wake-up interrupt. So what we need to do is we need to activate the interrupt. So in the NVIC setting, I click on enable here. Just before I switch to the next IP, I go back to the top drawing to again explain what we have done so far. So we have configured the comparator, the ultra low power comparator, to receive the PWM signals on PA1 and compare it with 1.2 volts. We have sent then the reshaped signal to the channel 1 and channel 3 of the low power timer in order to capture the edge, the falling edge on channel 1 and rising edge on channel 3. We have also configured the RTC to generate wake up every second, and that's it. So now, in fact, what we need to do is we need to finalize the project. So it means to configure the clock tree, because so far we have not said what was the clock of the RTC, the clock of the core, and the clock of the low power timer. And you will see how we will tackle also the LCD. So I go back to the CubeMX configuration. So we have finished for the RTC. We go to the next part, which is the clock configuration. And the clock configuration, what we will do is we will select the MSI 2 MHz because this allows to use the low power regulator, and core will be clocked in what we call a low power run mode in this case, so which is 2 MHz maximum frequency. We will select LSE for the source of the RTC and the source of the LCD. And we will select also LSE for the source of the low power timer 1. So let's do that. So you go to the clock configuration. It's a nice feature of CubeMX because you have all the clock tree of the chip here. It's very convenient. So you select 2 MHz for the MSI, and you select the MSI as the source of the system clock. You select the LSE for the RTC and the LCD clock. And regarding the low power timer, you need also to select the LSE. And that's it. So going back to the cheat sheet, you see that the only last step that we need to perform is to select IDE that we want to use. By default, it's IAR that is proposed. So here we will take Cube IDE, and we will generate the project. And we need also to put a name of the project. So I will put it in a temporary folder. I will set name that it's end device workshop. And for the IDE, I will select Cube IDE, and I will generate the code. So it's asking me if I want to open the project. I open it. So the end device has been generated, and it's visible here in Cube IDE. So I will switch now to the Cube IDE coding part. So you see that we have 11 steps to complete here. So the first one was to open Cube IDE, so this is done. The second step is to add the board support package and the low-level library. So indeed, the LCD, it's an external component. See it here, it's an external component that is mounted on the discovery kit. And each time there is this kind of external component on the ST boards, the software utilities to drive these components is systematically put in what we call the board support package on the Cube firmware. And this is very convenient way to drive these external components. The point is that so today, in the current existing CubeMX version, there is no click button possibility to add the board support package inside your project. It's ongoing, so it will come soon in a new release of CubeMX, but today we have to manually add the board support package, so this is what we are doing here. And also, because we want to optimize a bit the software, we will use low-level driver. By default, here we got some HAL that are used in the code, and you will see that we will, in some places, we will use low-level driver, which allows to get a bit more optimized code. So I copy this set of include file, and I will put that in the main.h in the user code begin include. So you see that in each .c or .h file, you have some beacon, user code begin, user code end, and this is where you need to put the additional code. This way, if you regenerate the project from CubeMX, all this code will be kept. And you see that here it's complaining because it doesn't know where these files are located. This is normal because this is the board support package file, and for the moment they are not part of the project. What we will do also, because we are using the LCD and the board support package is using the HL driver of the LCD, so we need to enable the HL manually, the LCD HL manually. So for this, you need to uncomment in the HL conf.h the LCD. So it is here. Okay. Then we need to copy the missing board support package file. So the first thing is to go to the board support package repository on the Cube firmware. So let me open it, my side. So I am here in the, by default, CubeMX or CubeIDE are downloading the Cube firmware and putting that on your PC, in your user space in STM32Cube repository. So you can see that here I have plenty of Cube firmware because I use many STM32 boards. And inside the U0, so the Cube firmware structure is always the same. It looks like this one. And inside the driver folder, you have a folder for the HL and low-level driver and folder for the board support package. And inside the board support package, for the discovery kit, you have the file that we would like to add in our project. By default, the conf.h file is, in fact, does not exist. It's a conf_templates.h file that exists. And what you have to do, you have to copy paste this file and rename it just remove the template. It's exactly the same file here. Okay, so what now we have to do, we have to copy the missing file. So this part is already done. It's to rename the conf template in conf.h. And now what I need to do is I need to drag and drop these 4 files inside my include folder. Okay. So the glass LCD.h, this one, the discovery.h, this one, the conf, and the error. This one. Okay. And I need to copy that inside the include folder, my project. Copy the file. Now they have been added. Okay, and I need to do the same with but this time it will be in the source folder that I want to do the copy of the glass LCD.c. So the glass LCD.c, it's this one. And I want to copy it inside my source folder. Okay. This is good. And go to the next step. We have activated the HL of the LCD inside the configuration file of the project, but we have not yet added the .h and .c file of the HL, so we need to do that now. So I need to go back to the driver folder and enter into the HL driver folder. And here I will find inside the include folder the HL LCD.h that is somewhere. It's here. And I need to copy that. I will put it in with all the other HL that have been added by CubeMX inside the project. So here for the .h, I will put it inside the include. Okay. It has been added, I hope, yes. And I will do the same for the HL.c. So HLLCD.c, I copy it and I put it in the source It's here. Okay, good. And at this point, normally it should compile because I have added the board support package, all the necessary files that the board support package needs. So we can try to compile this intermediate step to see that everything is okay. Good. No error. So we can continue. Okay, so it's a minor point because I guess that if you order a discovery kit, normally today you should get revision C, but on the older revision and it could happen that in the future there is also a new revision. The LCD, so you need to select the proper revision of your discovery board, especially for the LCD. It's a different reference of the LCD that is mounted on the discovery kit. Depending on the board revision. So for the board support package, you need to have the proper revision. So here it's, in my case, I have a revision C of the board. Okay, you see that it's revision C here. Let's double check that it's the good one. You see in my case, it's revision C, so everything is okay. So I can continue. So we have almost completed, and we have at part 6 of 11 for the code addition in the project. So we are only 5 remaining page 2, and the project will be finished. So be patient. We will add some proprietary or let's say private function that we will use to process the interrupt from the low power timer and interrupt from the RTC. So I copy this section of code and I put it in the user code begin external function prototype, main.h. So this is for the declaration. So this callback, so the one of the RTC and the one for the low power timer, you see the capture rising callback and the capture falling callback. I need to call this callback in the interrupt subroutine. And in fact, we are doing that in a bit different way that for the people who are used to use STM32 ecosystem, usually there is a weak callback that you can overload to put your own callback. But doing that, in fact, you will need to enter into the HL code that is processing the interrupt. This HL is an exhaustive code that is taking into account all the possible flags that could be raised when an interrupt occurs. In our case, we will simplify this. We will just check that it's the good wake up flag or capture compare flag for the low power timer that is activated. And we will clear this flag using low level driver and we will call our callback. So for that, we go to the interrupt subroutine. So all the interrupt code generated by CubeMX is always on this kind of file, interrupt.c. And if you go at the end, you will find, because we activated inside CubeMX the NVIC for the RTC and the NVIC for the low power timer, you have this code that is available. So we will comment out the HL call. And we will replace that by the code that is indicated in the cheat sheet. So for the RTC, one, checking that the flag is set, clearing the flag, calling the callback. And for the low power timer, So it's bits the same, checking that it's a capture compare falling flag that is set, so which is the channel 1, and call the capture compare falling callback. And or if it's the channel 3, then call the rising callback. Okay, and then clear the flag, clear the interrupt flag. That's all for the interrupt. And now in the main.c, for the main processing of all this, we need to add some global variable. So one that will store the new value of the capture compare register each time there is a rising edge that occurs. And one to store the duty cycle of the low pulse. So let's copy that and put it in the private variable section of the main.c. So main.c, in the private variable section, I put this global variable. Okay, go back to the cheat sheet. There is a prototype function that, the name is clear enough. It's converting integer to character. So this will be used to display value on the LCD. Copy the code, and I put it in private function prototype. And now I enter in the main loop, or in the main procedure. I copy, so this code I can explain. So I will just first copy it and then explain. So I put it in user code begin init inside the main.c. So user code begin init here inside the main.c. You see, we are just after the HL init. So what we do here, in fact, you remember we said that inside the RTC, we want to have some alarm, some wake ups that is programmed. And I said that the RTC, it's powered by the backup domain. And so if you have a reset, if you have just or just the main VCC that disappear, but not the VBAT, you will keep the configuration of the backup domain and the configuration of the RTC. And so we don't want that, because we want, when we start from the reset here, in our case, we want to clean everything and to be sure that the RTC is back to its virgin state. So what we do, we clock the power IP. So power, it's an IP that is in charge of all the power stuff of the U0. So we enable the clock of this IP. Inside this IP, you need to first enable the access to the backup domain that is protected. And when you have done that, you can set a bit to force the reset of this backup domain. And in order to be sure that the reset is done before you continue, you do a polling of the LSC ready flag that will be set when all the backup domain has been properly reset. And then you release the reset of the backup domain. Another small piece of code that we need to add is inside the initialization of the RTC. It's to temporarily deactivate the wake up timer. You remember that in CubeMX, we have activated this timer. So by default, when you do the init of the RTC, it will be activated at the end of the init, when you exit from the init. And in our case, for our processing, we want to activate this interrupt only when we start to detect some falling or rising activity, some edge on the PWM. So for the moment, in order to achieve that, for the moment in the init part, we will deactivate the wake up timer. So if you go inside the main.c, so it's below, it's where you have all the inits that has been added. So the comparator 1 init, it's not this one, LP team 1, it's not this one. So RTC init, so this is the one. And at the end of the inits, so you see that we set the wake up timer, and just end of the init of the RTC, just after the setting of the wake up timer, we deactivate it. Let's go back. Now we will we continue in the main.c file. And what we want to do is to configure the glass LCD. The U0 segment LCD, it's also really well designed for ultra low power. It can be clocked by the 32 kilohertz, and you have seen that we were activating the 32 kilohertz as a clock source for the LCD in the clock tree of CubeMX. It can work even in stop 2. So this is why also in the demo of Jeff, you were seeing that the luminosity of the photovoltaic panel was still displayed even if the core was in stop 2. It has an ultra low power consumption, approximately 1.5 microamp at 32 kilohertz. It can have up to 8 COM and 48 segments. So it depends on the package. Here you have to check in the datasheet. If you use a very small package, you will have less segments. Or you can have also 4 COM and 52 segments if you want. You have, regarding the bias of the signal, several possibilities. Can be static, 1/2, 1/3, or 1/4. I let you check on inside the reference manual. You have nice drawing explaining what it means. It's a bit complex, so I will not lose time on this. Here in the drawing, here you have 2 COM lines that are used, in fact, by the way, and the one segment that is shown here. And you have, in fact, 1/2 bias. So, in fact, you have a ground VDD and half VDD, half VCC, sorry, VCC and half VCC that is visible on the line. But I let you double check in the reference manual, in fact, all the nice drawings that we have on this topic. And very important, you have an integrated step-up that allows to keep a very stable VLCD, even if you are powered by a battery. So if your battery voltage is falling, the VLCD voltage will be still at the same level, which is very important for the quality of the display. And you can select 2.6 to 3.51 volts for this VLCD. And here a small drawing, the last part, it's a small drawing to recap or to remind you what a segment LCD looks like. So in fact, you have 2 electrodes, one for the ground and one for the voltage, I would say. And when you have a voltage that is applied on the voltage electrode, the liquid crystal gets oriented or not. And this allows to either see a dark pixel or nothing. Okay, and the characteristic of this technology is that it's a passive matrix, so there is absolutely no transistor at all. It's low cost, low consumption, and what you need to know is that you need 1 pin per segment signal. So I let you double check okay, what it means when you have 8 COM or 4 COM or 1 COM. So depending on this, 1 segment signal can be used to drive several segments in practice. But anyway, you need to remember that to display many information on an LCD, you will need many pins. Okay. But it's ultra low cost, ultra low consumption. And if you look at the block diagram very quickly, because in fact we are using everything of the block diagram, you see that we have the 32 kilohertz that is coming to a frequency generator here, and that will generate the variable frequency that will drive the LCD, drive the COM and segment pin of the LCD. You have the voltage generator, so the step-up voltage generator that can generate all the needed voltage for your segment LCD. In our case, we will use VSS, 1/3, 2/3, and VLCD. So it's a 1/3 bias that we are using. And you have also the possibility, you have several additional subtlety inside the LCD driver that allow to temporarily have a high drive when you start to, you have some voltage change on your segments and COM signals in order to improve the contrast of the LCD, even in a low power mode. Okay. Everything is described in the reference manual, so I will not dig more into this because time is running. So let's switch back to the code. So here we are using the board support package to drive these components. So I copy the code and we put that in user code begin 2. Go back above. So this code is so calling the board support package to do the initialization of the glass LCD. It's clearing the glass LCD. So because the clock system is 2 megahertz, this is what we have set in CubeMX, we can enable the low power run mode, so using the low power regulator. We will here enable the comparator, the ultra low power comparator, start the channel 1 and channel 3 of the low power timer. We use the board support package to display the message, waiting for signal, etc. So it's a kind of initialization message. Then we clear it. We modify a couple of settings on the LCD, on the glass LCD, in order to improve the consumption. So we set the contrast level. So in fact, it's the VLCD that you are tuning. So it's the step-up frequency that you are tuning to select a voltage that is not too high. We disable the high drive, so meaning that there are 2 resistor ladder in the LCD with different resistor value. Here we take the highest value to reduce the power consumption also, but doing that, we also use what I said, it's the pulse-on duration, so it's the capacity to have, when there is the voltage transition on the COM and segment line, to have a small pulse that is still at a high drive, just to improve the contrast. And we display the idle message. At this moment, the core is still in a low power run mode because we activated it. So what we want to do is we want to enter in stop mode. We will not enter in stop to mode in this example because when you are in low power run, you cannot enter in stop 2, you need to enter in stop 1. The reason is simple, it's because when you exit from stop 2, there is current rush that is too big for the low power regulator. So the transition is forbidden from low power run to stop 2. So here we will so use stop 1. And we are using also the feature of the Cortex that is called sleep on exit. It means that when you are in stop 1 and there is an interrupt, you will process the interrupt, and then you will immediately go back to the stop 1 without any need to enter again in the main.c loop to call again the HL power enter stop 1 mode. So in fact, we will enter only one time into this procedure here, enter in stop 1, and then everything will be processed under the interrupt. So either the LPTIM interrupt or the RTC interrupt. And we will go back immediately to stop 1. So I copy that. We go back to the code. And you see, I put this just after the previous line of code. So I'm not in the while loop, I'm just entering in stop 1 here. And the last part is the processing code. So it's a quite simple code. In fact, you remember that we put in the interrupt.c to the callback, capture falling callback, capture rising callback, and RTC wake up callback for the RTC. And here in the main.c, we put the contents of this callback. And the principle is quite simple. In fact, we check in the capture falling. So first in the capture rising, maybe we just update the new value of the rising edge. Okay, this is the only thing we do. And in the capture falling, in fact, we update. We have the old value of the falling, so this one. We have the new value of the falling, so this one. And we use also the one that has been captured in the rising edge, so the value of the rising. And we compute like that if there is a modification, if there is an activity that is detected, in this case, we enable the wake-up interrupt of the RTC, okay? And we compute the duty cycle because we have valuable information here in all these three values. So we can have the duty cycle that is computed, and we activate the RTC. Normally, we should compute all the case because the low power timer one, it's a 16-bit timer. So there is, at a given point in time, there is a rollover of the timer. So there could be some complex case where you have the new value that is lower than the old value. Here we compute only, because it's just a simple example that we want to do. We compute only the case where we have the new value that is bigger than the new value falling, that is bigger than the new value rising, that is bigger than the old value falling. For a real project, you would have to take into account all the cases. Okay. So let's copy that. And we put that in the main.c at the end in the section that is made for all the callback. Okay. And the last is the last section to copy. I copy it and I explain. It's also in the user code begin and for. So we have here the core of the integer into char conversion. So I will not describe it. It's very interesting. And we have the RTC wake up callback. So the RTC wake up callback, you have seen that we were activating it in the falling edge interrupt when there is an activity that is detected. And the wake up callback so will be triggered every second, and because this is what we program for the RTC. And so every second we will enter into this callback and we will check if the low power timer is still getting some activity. So we check if the value of the edge are moving. If it is moving, we will then display, so you have this convert integer into char that is called to convert into a character the duty cycle. And we will, so it is putting this duty cycle in tab 4 and 5. And in tab 0, 1.23, we just print duty cycle, double dot, 0, and then you will have the duty cycle. So this is displayed in case of the activity is detected. And if no activity is detected, so meaning that we are back to idle, we display idle on the LCD. And we disable the interrupt of the RTC. That's all. So let's compile all this. No error. And let's try. Okay. Okay. Yeah. So one thing I will do is, in fact, in the project property, I will set the optimization for speed because this improve the execution time, and so it improves the consumption. And in the debug configuration of the debugger, sorry, I will disable the debug in low power mode to avoid to keep part of the IP activated, and that also increase the consumption. Okay, I was too fast. Okay, so you see that we have the welcome signal that is displayed, and just after that, we have the idle that is sent. I will. Okay. So I power the discovery kit. So you see that we have this welcome message that is shown. Okay. And I power the master panel. And if I press on the button of the master panel to change the duty cycle, so here I am at 20%, I will change it again to 40%, change again to 60%, and I will go back to the idle mode. Okay. And the idle mode, it's the 1 second interrupt that's detected, so this is why it's a bit long to get the idle that is detected. Okay, and now I will measure the consumption, so I will power the discovery kit with the ST-Link V3 power. So I unplug the reset here, which is this switch here. I will put the power line coming from the ST-Link V3 power here. I'll start the cube monitor power. And I start the acquisition. So you see that here we have the welcome message that is displayed. And then we go to the idle mode, and you see that you have this consumption here that is extremely low here. So we are approximately at 7.5 microamp here. If now I press on the PWM signal to send the PWM signal at 20%, for example, you see that you have a small increase in the power consumption here. You see that every second you have the RTC interrupt that is triggered. Okay, and this is what is displaying the duty cycle at 20%. If I continue I will put the acquisition time to infinite. So if I press again on the duty cycle here, I have now the duty cycle at 40%, still the same consumption. I press again, I have the duty cycle at 60%, still the same consumption. And if I press again, the duty cycle will be now idle. In fact, there is 0% duty cycle. You see, okay, I should have, let's do it again, because it was a bit too fast. Maybe I will go back to a 10-second acquisition. And I will do all the three, so 40%, 60%, and I go back to idle. Okay. So you see, in fact, when you start to have some edge, PWM edge, you have the LP team interrupt that is coming very regularly, so the consumption increase. You also activate the RTC interrupt, so you have this RTC interrupt that appear here. You change the duty cycle, it's still a bit the same consumption because it's the same processing. You update under the RTC interrupt the duty cycle message. And when you go back to idle line, you stop to receive some LP team interrupt here. You still have the RTC interrupt. And the RTC interrupt will detect that there is no activity at the second one, and it will display idle and stop to get the RTC and stop the RTC interrupt. So this is what you see here, and this is what we have done. And you see the nice consumption, which is approximately 7 microamp. If I increase a bit the sampling frequency here to select something that could be a bit more. And yeah, sorry, and you also can activate the report. You see that when you are in idle, the consumption is around 7.4 microamp, okay, which is the expected one. So that's all for this hands-on. I hope it was not too difficult to follow.